Hi, I'm Mark Barsamian with the Ohio University Math Department. In this video, I'll introduce the concept of betweenness. First, we'll discuss betweenness for real numbers, and then I'll introduce the idea of betweenness for points in a metric geometry, and we'll do a couple of basic examples. This material is produced for Ohio University Math 3110 College Geometry. The reading for this video is from the first few pages of section 3.2, Betweenness, in the book Geometry, A Metric Approach with Models by Millman and Parker. The homework for this video is this short collection of 3 exercises from section 3.2. Recall some important concepts from section 3.1. One was the triangle inequality for distance functions. It's this inequality. The distance from A to C is less than or equal to the distance from A to B plus the distance from B to C. Now, if that inequality is true for all points A, B, C, then we say that that distance function on that set of points satisfies the triangle inequality. It's important to remember that not all distance functions satisfy the triangle inequality. In the previous video, we discussed the absolute value distance function on the set of real numbers. It's this distance function. The distance between two real numbers is just simply the absolute value of the difference between those numbers. And we showed that it does satisfy the triangle inequality. That is, this inequality is always true for all real numbers x, y, z. And that corresponds to this expression involving absolute value symbols. Also in the previous video, we discussed this proposition that the Euclidean distance function does satisfy the triangle inequality for distance functions. That is, for all points in the Cartesian plane, this inequality involving the Euclidean distance function is always true. An obvious question is, when does the triangle inequality for the absolute value distance function become an equality? The triangle inequality for the absolute value distance function is this. It's got an less than or equal to sign in there. So the question is, when is this true? That is, when is this expression true? Well, to answer that, let's consider some cases. There are 6 possibilities for the relationship between distinct real numbers x, y, and z. Here are the 6 cases. We could have x less than y less than z. We could have z less than y less than x. We could have y less than x less than z. We could have z less than x less than y, and so forth. Let's see what the triangle inequality becomes in each of those cases. This should say 6 cases. Well, the first case is when x is less than y less than z. We'll figure out that this equation is true by starting with just the left side, z minus x. We do a trick. We subtract and add something to that quantity. Notice we subtracted and added the number y, so that doesn't change the quantity z minus x at all. Then we can add parentheses without changing anything. Now, because this inequality is true, now here I see I've got a typo. Since that inequality is true, we know that each of these quantities is a positive number. So that means that each of those quantities in parentheses is the same as its absolute value. So we can replace that with this, we can replace that with this, and so forth. We can change the order of the letters inside the absolute values without changing the result, and we can change the order of the addition on the right side without changing the result. And we see that we end up with this equation. We see that the less than or equal to sign in the triangle inequality is actually an equal sign. Now, a similar case, case 2, is when z is less than y is less than x. We do similar steps, and we find that in that case, that equation is true as well. Now, what about case 3? When y is less than x is less than z. Well, we again do a trick. we subtract and add something, this time to the quantity z minus y. We go through a bunch of steps. I'll let you read them. The result is we end up with this strict inequality. So the less than or equal to sign that was in the triangle inequality is actually a strict less than sign in case 3. Now cases 4, 5, and 6 unfold in much the same way as case 3. In each case, we end up with a strict inequality. So we summarize these results in a nice green box. So the triangle inequality is this inclusive inequality, the inclusive less than. But in particular cases, in cases 1 and 2, the triangle inequality becomes an equality. In the rest of the cases, 3, 4, 5, and 6, the triangle inequality becomes a strict inequality. Now I want to talk about betweenness for real numbers. A central feature of metric geometry is the existence of a ruler for every line. This has many consequences. Because of rulers, all features of the real number line will have analogs on lines in a metric geometry. One important feature of the real number line that we'll want to use in metric geometry is the concept of betweenness. We'll define and explore betweenness for real numbers now in preparation for later defining betweenness for points in a metric geometry. So here's the definition of betweenness for real numbers. This symbol, x asterisk y asterisk z, is spoken y is between x and z. You use this symbol when x, y, and z are real numbers. And what it means is this or this. Either x is less than y is less than z, or z is less than y is less than x. Now, a quick remark, it's a property of real numbers that for any given 3 distinct real numbers, there's exactly one smallest, one largest, and the other is in between those two. So given 3 distinct real numbers, there's always going to be exactly one that you can say those words about. Y is between x and z. Now, betweenness of real numbers is related to the distance between them. Recognize that the inequalities in the definition of betweenness for real numbers, these inequalities, they showed up previously in the green box 2 pages back, involving cases where the triangle inequality becomes an equality or a strict inequality. So those 2 inequalities showed up in this green box. They were cases 1 and 2. Those were the cases when the triangle inequality actually is an equality. So those results in that green box can be used to prove this nice lemma about the betweenness of real numbers. So given distinct real numbers, x, y, z, the following are equivalent. I abbreviate that TFAE. This statement, x star y star z, that is to say y is between x and z, and this statement, the distance between x and z is equal to the distance between x and y plus the distance between y and z. That is this equation involving the absolute value symbol. So this lemma doesn't say that either of these statements is true. It says that those statements are equivalent to each other. That is, they're either both true or they're both false. Now I want to discuss the statement of the claim and the proof strategy. Most books state this sort of theorem as A if and only if B. I prefer to use the terminology of equivalent statements. Remember, my lemma is stated this way: the following statements are equivalent. Now the most common proof strategy is proof part 1, prove that if A is true then B is true, and proof part 2, prove that if B is true then A is true. But there are other things that you can do instead. So for instance, I find it easier to prove the contrapositive of that. So the contrapositive of that blue circled statement, if B then A, is this statement. If not A, then not B. So my proof structure for my lemma is going to be prove that if A is true, then B is true, and then prove that if A is not true, then B is not true. So here's proof part 1. Prove that if A is true, then B is true. So remember the proof structure. We're going to have in the first statement the hypothesis. So suppose A is true. And we're going to end the proof with the conclusion. B is true. Now we have to figure out how to bridge that gap. Well, if A is true, that means that x is less than y is less than z, or z is less than y is less than x. That's by what it means to say that x star y star z. That is, we've used that fact and the definition of betweenness. So we've just simply unpacked that defined term and we've written what it really means. But if this is true or this is true, then we can say that this is true because that green box 4 pages ago, in cases 1 and 2, we found that this equality was true. Let's go up and have a look. In these 2 cases, cases 1 and 2, when we had that inequality or this inequality, we had this equation true. So that's the end of our proof that if A is true, then B is true. Now, what about the proof that if A is false, then B is false? Well, the proof structure will be the same. We start by supposing the hypothesis, suppose that A is false, and we have to end by showing that B is false. Well, if x star y star z is false, that means that neither of these inequalities is true. That's by statement 1 and the definition of what this symbol means. If this is false, that means that these inequalities are false. Well, that must mean that either this inequality is true, or this one, or this one, or this one. Well, those are cases 3, 4, 5, and 6 from the green box 4 pages ago. Here's the green box. Those 4 inequalities are there. Cases 3, 4, 5, and 6. And we see that in each of those cases, the triangle inequality becomes a strict inequality. So we can just say that this strict inequality is true by all that work we did in producing that green box 4 pages ago. So there's our proof. We prove that if A is true, then B is true, and then we prove that if A is false, then B is false. So again, we prove these statements are equivalent. We didn't prove that either one of them is true. We just proved that if one of them is true, then the other is true. If one of them is false, then the other is false. Now I want to discuss some new notation. We're going to be ready now for betweenness for points in a metric geometry, but it'll be helpful to have some new notation. Recall this notation for the unique line containing 2 given points in an incidence geometry. This symbol, spoken line AB, you can use when you have an incidence geometry in the discussion and when A and B are 2 distinct points in that incidence geometry. What that symbol means is the unique line that A and B both lie on. Remember that in an incidence geometry, given 2 distinct points, there is exactly one line that they both lie on. Now there's some new notation for the distance between 2 given points. It's this symbol, AB, without anything over the top of them. Now this symbol can be used when there's a metric geometry in the discussion, and A and B are 2 points, not necessarily distinct. What this symbol means is the distance between A and B. So this symbol can be used anytime you are working with an incidence geometry. This symbol can only be used when you're working in a metric geometry. Finally, I'm ready to introduce betweenness for points in a metric geometry. Here's the symbol, A-B-C. It's spoken, B is between A and C. You use this symbol when A, B, C are points in a metric geometry. What it means is that the following 2 things are both true. A, B, C are distinct collinear points, That's one requirement. And this equation has to be true. That is, AC equals AB plus BC. That is, the distances add up. So for example, let A, B, and D be these points in the Poincare plane. Our goal is to show this, A dash B dash D. That is, to show that B is between A and D. Well, let's go back up and look at the definition. We have to show that this stuff is satisfied. We have to show that those are distinct points. We have to show that they're collinear. And we have to show that this equation is true. Well, clearly, those 3 points are distinct. They have different coordinates. It's also straightforward to show that they all lie on one line, this line, the line with center at 6, 0, and with radius 5. That's a type 2 line. Now we need to show that the distances add up, so we just simply compute the distance from A to B, the distance from B to D, and the distance from A to D. When we do all the arithmetic and simplify, notice we can simplify quite a bit. We end up with these numbers. The distance from A to B is ln of 2, the distance from B to D is ln of 3, and the distance from A to D is ln of 6. Now notice that I haven't given any decimal approximations for these. I'm just going to work with the exact symbols. Now notice what happens when I add up the distance from A to B and the distance from B to D. I add ln of 2 and ln of 3. Well, rule of logarithms, ln of A plus ln of B equals ln of A times B, allows us to replace this expression with this expression. But that's just ln of 6, and that's the distance from A to D. So we conclude that since the points are distinct and collinear, and the distances add up, that we can say that B is between A and D. Part B, illustrate the result from A. Well, here are 3 points. Notice my illustration shows the points labeled with their coordinates. Now, I didn't put the letters on my computer-made drawing because Desmos calculator won't let you do that. But I do have the XY coordinates shown clearly for those points. Those are clearly important points. I convey the fact that they're collinear by showing the line that they all lie on. Now, again, Desmos won't let me label things with letters, so I should add the annotation that this line is the line with center at 6, 0 and with radius 5. That's a type 2 line. Now, other important features that should be labeled, that type 2 line has a center because it's a semicircular shape, and it has these missing endpoints, is how I like to refer to them. So those are important points that should be labeled with their XY coordinates as well. Let's go on. Now I want to talk about the importance of collinearity in the definition of betweenness. Both requirements are important in the definition. The requirement that A, B, and C be distinct and collinear, and the requirement that the distances add up. It's possible for the second requirement to be true without the first requirement being true. And of course, it's possible for the first requirement to be true without the second requirement to be being true. So for instance, here's an example. Let A, B, and C be these 3 points in the taxicab plane. 2, 1, 6, 3, and 8, 4. Notice that those points are collinear because they all lie on the non-vertical line y equals 1/2 x. When we compute the distances, we find that the distance from A to B plus the distance from B to C is 9, and the distance from A to C is 9. So observe that that equation is true. The distances do add up, and the points are collinear, so we can say that B is between A and C. Those 3 points are plotted here at right. I should add coordinates to this, and I should label this line. So there's no surprise here. Now in part B, let A be again the point 2, 1, and let C be again the point 8, 4, but let D be the point 8, 1. Notice that those points are not collinear because A and C lie on this line that's shown here, but A and D, this should say lie, they lie on the non-vertical line y equals 1. It's a horizontal line. And C and D lie, this is another typo, on the vertical line x equals 8. So those points are not collinear. Even so, when we compute the distances, we find that the distance from A to D plus the distance from D to C is 9. And that's the same as the distance from A to C. So the distances add up. But those points are not collinear. Since those points are not collinear, we say that ADC is false. Now let's make an illustration. Here's our point A, here's our point C, and here's our point D down here. Now you can see why this weird thing happened. The distance from A to D is this length, 6. The distance from D to C is this length, 3. The distance from A to C is the sum of those lengths, 9. So you can see why the distances add up. But even though the distances add up, A, D, and C are not collinear. The line that A and C lie on is not this stair-step shape. The line that A and C lie on is the Cartesian line. Cartesian lines are not stair-step things. When we compute distance in the taxicab plane, we sometimes draw pictures involving stair-steps, but those stair-steps are not the line that A and C lie on. The line that A and C lie on is that slanting line. The line that A and D lie on is this horizontal line, and the line that C and D lie on is this vertical line. So those are not collinear points, even though the distances add up. And so we do not say that D is between A and C. That's false. Okay, that's the end of this video. Thank you.